So, last class I have discussed about the pile load test. Now, this class I will discuss how I will get the allowable bearing capacity of a pile from the obtained load versus settlement curve based on the IS code. So, as I mentioned, as per the IS code, the allowable load on a single pile shall be lesser of the following. So, carefully you read these two clauses, that 2/3 of final load at which total settlement attains a value of 12 millimeter. If nothing is specified, then the permissible settlement of a single pile is 12 millimeter, or if any other permissible value is specified, then load shall be corresponding to that actual total settlement. So, that means, if we have a load settlement curve like this is load and this is settlement. Suppose that this is the 12 millimeter settlement. So, you have the corresponding load is Q 1. Okay. So, it is saying that first case your Q allowable 1 is equal to 2/3 of Q 1. If nothing is specified, then 12 millimeter will be treated as a permissible settlement of single pile. Okay. And the clause 2, this is clause 1, and the clause 2 is 50% of final load at which total settlement equal to 10% of pile diameter in case of uniform diameter pile, or 7.5% of bulb diameter in case of under rim pile. Okay, suppose if you have a pile diameter of 300 millimeter. Okay. So, suppose if the pile diameter is 300 millimeter, then 10% of 300 millimeter, 10% of 300 millimeter is equal to 30 millimeter. So, suppose this is your 30 millimeter. Okay. So, you have the corresponding load is Q 2. Okay. So, as per the second clause, your Q allowable 2 is equal to 50% of that Q 2. So, half of Q 2. So, your Q allowable will be minimum of Q allowable 1 and Q allowable 2. Okay. So, that means your Q allowable load carrying capacity of the pile minimum of these two load. So, this is the clause as per the IS code. So, we will use this clause to determine the allowable load carrying capacity of a single pile. This is the clause for the single pile. Okay. Now, next clause for the group pile. This is for the group pile. The similar type of clause, the final load at which total settlement attains a value of 25 millimeter. If nothing is specified, the permissible settlement for the group you can take as a 25 millimeter. So, that means that suppose you have a load versus settlement curve. Okay. So, this is load versus settlement. So, you have a, this is say 25 millimeter. So, this is the Q 1. So, as per the clause 1, your Q allowable is equal to Q 1 as per the clause 1, and 2/3 of the final load at which total settlement value is 40 millimeter. Suppose this is 40 millimeter. So, this is Q 2. So, as per clause 2, Q allowable is 2/3 of Q 2. Okay. So, your actual Q allowable, this is Q allowable 1, this is Q allowable 2 is minimum of these two. Okay. So, minimum of these two will be your Q allowable. So, this is for the group pile. So, now I will solve one problem on a single pile, that the example problem is the following data was obtained in a vertical pile load test on 30 millimeter diameter pile. Determine the shape, determine the allowable or shape load as per IS 2911 part 4 1979. So, those clauses are from this code. Okay. So, those clauses are from this code. So, this is the load which was applied 50, 100, 200, 300 up to 600, and this is the measured settlement. Okay. So, I have drawn this curve. So, this is the load which is kilonewton, and this is the settlement which is millimeter. Okay. So, this is the kilonewton in this side, settlement in downward direction. So, this is the curve, you can see corresponding to 600, this is the 70 millimeter is the settlement. So, my first clause as per IS code is that 2/3 of 12 millimeter, I mean load corresponding to 12 millimeters. We will take 2/3 of that. So, my 12 millimeter is this is the 220, this is 230. So, 12 millimeter is somewhere here. Okay. So, this is 12 millimeter. Okay. So, this is 12 millimeter. So, corresponding load is this one. So, my Q1 is equal to 230 kilonewton. So, the clause 1 I will take that my clause 1 that Q allowable is equal to 2/3 of Q1. So, 2/3 Q1 is 230. So, this is equal to 153 kilonewton. This is clause 1. Okay. Now, second clause that 50% of load corresponding to the settlement of 10% pile diameter. So, pile diameter is 300, 10% of that is 30 millimeter, it is 300 millimeter, 10% is 10% is equal to 300 millimeter, 30 millimeter. So, 30 millimeter is here. So, the corresponding load is here. So, this is the corresponding load, or this is the Q2 which is equal to 400, this is 400, this is 10, 410 kilonewton. So, as per clause 2, Q allowable is equal to 50% of Q2. So, this is half into 410. So, that is equal to 205 kilonewton. Okay. So, your Q allowable will be equal to minimum of these two. So, 153 kilonewton. So, from the pile load test I am getting the Q allowable value directly is 150 kilonewton. Okay. So, this similar way we can determine the allowable load carrying capacity of group pile also. Okay. So, but these tests are on continuous test, because here this data is continuous, you can see. So, here I will get only the Q allowable, but I do not know what is the contribution of tip resistance and the friction resistance separately in this 153 kilonewton. But if I want to know the separately the friction and the tip resistance, then I have to take the help of the cyclic pile load test data. Okay. So, the next part I will discuss that how I will use the cyclic plate load test data, and from there I will get the friction and the tip resistance separately. Okay. So, that means it is required when it is carried out, when it is required to separate the pile load into skin friction and point bearing. Okay. That means the King's friction resistance or resistance from the King's friction and the point bearing on a single of uniform diameter. It is limited to the initial test only. Okay. So, that means it is on the test pile only. So, what is the process and how I will cyclic pile load test? So, we have, suppose this is our load versus settlement plot. Okay. So, this is the load which is applied on pile top, okay, which is applied on the pile top, and this is the settlement. Okay. So, as I mentioned that you are applying the first increment. So, that increment is say q 1, q 1 is the first increment. So, your load will be, this is the loading part. Now, you will go for the unloading part, you unload that q 1, then you will apply the second increment, that is q 2, again you apply the loading, okay, then again you will unload this part. Then you will apply the third increment q 3. Okay. So, you applied the third increment, again you will unload that. Okay, and so on. So, this is the cyclic test, loading versus the settlement plot. So, now this is the, if you look at this settlement plot, the load settlement plot, that when you are unloading this load, some settlement is recovered, because for example, if I go to the q 2 part. So, suppose this is the, during the loading your total settlement is this one. If I taking the second part, this is the say S T 2, S means the settlement, T is the total, 2 is the for second increment, okay, or second applied load. So, this is the S T 2 is the total settlement. Okay. Now, when we are unloading this, now when it is 0, it is not going to the initial position again, there is some deformation, okay, and that is the permanent deformation, that is your this much amount. So, this is, and then some amount is this much amount. Okay. So, if the total settlement. So, that means there is some recoverable settlement. So, that settlement is called the plastic settlement. So, what is, and the portion which is recovered is called the elastic settlement. So, now if we have a say load versus settlement curve, if this is like this and if you unload this, then it will come back again, then this total settlement is called the elastic settlement. Okay. So, that means the elastic settlement is the portion which is recovered, and the plastic settlement is the permanent settlement which is not recovered. Okay. So, it is the permanent deformation. So, here also this total settlement, it has two parts, one is the plastic settlement and one is, suppose this is S P 2 plastic settlement, or then sorry, this is SP2 is this one, SP2 is this one, this is SE2, because this is the elastic settlement which is recovered, SE2. Similarly, for 1 also, this is the, suppose this is the total settlement ST1, okay, and this settlement is not recovered. So, it has two part. So, this one is called SP1 and this is SE1. Okay. SE elastic settlement means the settlement which is been recovered, and plastic settlement the settlement which is not recovered. Okay, that is a permanent deformation. You can see there is always a permanent deformation as you increase the load. Okay. So, that means here this portion of settlement is recovered. So, it is elastic, and this portion settlement is not recovered, which is plastic. Similarly, here this portion of settlement is recovered, which is elastic, and this portion of settlement is not recovered, which is plastic. So, I can write that the total settlement is SE plus SP. So, S, or you can write ST. ST is the total settlement, SE is the elastic settlement, SP is the plastic settlement. Now, this total settlement I can write in this way, that is the del L plus SB. Now, what is del L? What is SB? So, the total settlement that I am getting, I do not know that what is the amount of deformation of the pile and what is the amount of deformation of the soil below the base of the pile. Because when I am applying a load on a pile, there is a possibility the pile material can settle and the soil below the tip of the pile, that will also settle. So, this total settlement is the summation of the pile material settlement and the soil below the tip of the pile settlement. Okay, so, that I have written ST is the del L is the, where del L is the compression of pile, compression of the pile or the pile material, and SB is the compression of the soil at the pile base. So, that means, if this is a pile, if we apply the load, so pile material can settle, that is del L, and the pile, this soil can settle also, that is your SB. So, the total settlement is the summation of SB and del L. Okay. So, SB can be again SE bar plus SP bar. So, the soil settlement, it has also elastic settlement part and the plastic settlement part. It has two component, because in the soil also it can be the elastic, it can be the plastic. Okay. So, that I have written that SB is also the elastic part and the plastic part. So, where your SE bar is equal to the elastic compression of the soil at base or pile base, and SP bar is the plastic compression of the soil at base. Okay. So, finally, I can write that ST is equal to del L plus SE bar plus SP bar. Okay. So, this is my one first equation number 1, this is equation number 2. Okay, this is the elastic settlement of total including. So, what is the difference between AC and AC bar? AC bar is the elastic settlement of the soil only and AC is the elastic settlement of the soil and pile material. SP is the elastic settlement of soil and pile material and SP bar is the SP is the plastic settlement of soil and pile material and SP bar is the plastic settlement of soil only. Okay. So, if I compare these two equation 1, then I can write that SE plus SP, this is equal to del L plus AC bar plus SP bar. I can write that. Okay. So, from here I can write AC bar is equal to SP minus SP bar plus AC minus del L. Okay. And it is quite obvious that when we apply the load on a pile, the pile settlement will never reach the plastic state. Okay. Soil, because pile is a very rigid material. So, when you apply the load, so it will never reach to the plastic state, it may reach to the elastic zone only. So, that means the pile settlement is always recoverable. Okay. So, that means the plastic settlement that you are getting, the total plastic settlement, that plastic settlement is due to the soil only. Okay, because we are assuming that the pile will never be in the plastic zone. So, that means here pile material. So, plastic settlement, if the plastic settlement of pile is neglected, then definitely SP will be equal to SP bar, because all the plastic settlement is due to the soil plastic settlement. So, I can write this equation AC bar, because this will be 0, SE minus del L. Okay. So, SE I will get from the load settlement curve. So, SE I will get from the load settlement curve corresponding to different, because this is the SE or this AC value for first load increment Q1, this is the AC value that I will get. For the second load increment, this is the AC value. So, this AC value I will get from this curve, that I will get from the final product of the cyclic load test. So, AC value I will get from the curve, but del L value how will get that? Del L is the compression of the pile material. Okay. So, del L value I will get by using this expression, del L is Q minus QF divided by 2 into L divided by AE, where Q is the load on the pile, QF is the frictional load, L is the length of the pile, A is the average cross section area of the pile, and E is the modulus of elasticity of the pile material. Okay, which is similar to that you apply if you apply a load P and length is L and A is the cross section, E is the elastic modulus, then you will get that my del L will be P L divided by A E. the similar thing is applied here. But here I mean total load which is Q is applied on the top, but as some friction component is there. So, it is subtracted that friction component, that means it is that only that tip component is giving that del L part. So, that is the idea, some friction component is deducted. So, that is the expression. So, now I will do the how I will calculate, I will explain how I will calculate the pile load capacity separately. Now, the next stage, so what I will do, so I will take a new curve. Okay. So, here it will be the load on pile top, and here it is S E bar, remember that this is AC bar. So, I will get this equation 3, I will get the AC bar, AC I will get from this curve, AC I will get from this original curve, and del L I will get from this expression. So, AC I am now this curve I am plotting load on pile top versus AC bar. So, first step 1, okay. Step 1, assume that your del L is equal to 0. The first one, assume that del L equal to 0, that means del L is equal to 0. If del L is equal to 0, then we have AC bar is equal to AC, AC I will get from the original curve. So, what I will do? I will draw a graph. So, from the say suppose you have a increment Q1, Q2, Q3, Q4 and so on. So, from this original graph corresponding to Q1, Q2, Q3 and Q4, you will get the AC value. That AC value will be equal to AC bar for your step 1, because we have assumed that del L equal to 0. So, we will get this type of curve. Okay. So, this is my first curve. This is we are getting from step 1 or step 1 I am getting assuming del L equal to 0, but this is not the actual or correct curve, because I have assumed that del L equal to 0, but there is definitely some del L value. So, that I have to incorporate in the next trial. So, this is my first trial. I got this curve corresponding to this Q1, Q2, Q3, Q4 and AC bar. So, what I will do now? So, now I will draw a line which is parallel to the straight portion of this curve. So, we have a straight portion of this curve. This is the straight portion of this curve. So, you draw a line which is parallel to the straight portion of this curve. Okay. So, this is draw the parallel to the straight portion of this curve. Fine. So, now, but this is incorrect, this curve is incorrect, because we have assumed del L equal to 0. So, this curve, the state curve is the parallel curve to the state portion of this curve, curve 1. Now, what these things indicates? This thing indicates that for a particular depth, this will be your Q Pu and this will be the Qf. Okay. This will indicate this will be this portion. So, which what does it mean? It means that if you look at this curve, that after some certain point this curve is parallel to this one. So, that means your after certain point your Qf value is not changing, only Q Pu is changing. So, it means that when you apply a load on a pile, first your frictional resistance is mobilized. Okay. During that portion, it is not that your Q Pu is exactly 0, but the friction part is first is mobilized, then the tip resistance or bearing part is mobilized. So, you can see depending upon the type of the soil where you are testing, this curve may change. This is not, I have drawn it. Okay. So, that means it may not be in the proper scale, depending upon which soil you are testing, you will get the proper curve. So, but the procedure I am explaining. So, this is the curve. So, you can see after certain point here, suppose this point, your friction resistance is no, because here the friction resistance, here the friction resistance, this portion the friction resistance, this portion friction resistance, this portion friction resistance is same, it is not increasing, only the tip resistance is increasing. That means after this point, your at this point your friction is fully mobilized. Okay. So, then only the tip resistance will increase if you load further. So, this is very important observation, that when you apply a load on a pile, first friction is fully mobilized, then the tip resistance will starting mobilizing. Okay. So, that is very important observation. So, now in the step 2, because this curve is not correct. So, what we will do in the step 2, now from this curve at any load, suppose this is my load, I can get what is the QF1 and what is the QPU1 for any loading from this curve. Now, you take that QF for corresponding to Q1. Now, you put this equation. Suppose you are doing del L for fast loading. So, del L will be Q1 minus QF1 divided by 2 divided by LE, and this is L. So, you will get for the for Q1. Okay. In the step 2, take QF from the curve. So, corresponding to Q1, this will be the QF. So, you put this Q1 minus QF from this curve you will take, and you will get a new delta 1. Now, you put this delta 1 here. Okay. Then you will get a new AC value. Now, you plot this curve again. Okay. So, when you plot this curve again, so I am using a new color. Suppose if I use the new color, so I will get another curve which may be like this. So, this is from step 2. Okay? And again it has a straight line, straight portion, extend that. Then again draw a curve which is parallel to the straight portion of this step 2 curve. Okay? Then in the step 3, again you calculate the QF value from this curve the same way. Okay. And again you draw another third curve. Okay. So, that may be like very close to this one. The blue one is third curve, which is getting from step 3. Okay. Step 3, again take QF, new QF. This is also a new QF from the curve. Okay. And again you draw the straight portion of this curve. So, this is number 3 again corresponding to number 3. This is corresponding to 2. This is this is corresponding to 1. So, you repeat this continue this process unless 2 successive curves overlap each other. Okay. So, once this is overlap each other, then that is the correct value, because you are doing a trial and error process, and then any point your these things will give you the QPU and these things will give you QF. So, we will get separately the friction resistance and the tip resistance. Generally, it is observed that up to after the 3 trials you will get both the trials are 3 to 4 trials. You will get these are overlapping to each other. So, you then from this curve you will get separately what is the Q P U and what is the Q F, and that is the ultimate. If you want to get the safe Q safe, Q P U safe, then you from this point you multiply it with the factor of safety. Okay. Similarly, friction also, that for the safe you multiply with the frictional force F divided by F. Okay. So, you multiply it with this force. The force that you are getting, you divide it with the factor of safety. So, if you want to get the Q safe, then Q P U divided by the F, or you can write here that your Q P U safe will be Q P U divided by the F, which is 2.5. Okay. And similarly, Q F safe is equal to Q F divided by F, which is also 2.5. So, this way we can determine separately that what is the pile resistance, what is the friction resistance and the tip resistance separately for a particular load. Suppose this is your particular load, and from the load, this load, what is the contribution of the friction and what is the contribution of a tip or bearing, that you can get separately from this cyclic pile load test data. So, that I have discussed, and another important thing is that from this study we know that first your friction resistance is fully mobilized or mobilized, then the tip resistance is mobilized. Okay? That is a very important information you should remember. So, in the next class, so this is the pile load test I have finished. In the next class, I will discuss the third method by which we can determine the pile load carrying capacity, that is the dynamic formula. Thank you.